3, 2, 1. All right. Well. Let's go backwards. Okay. So let's get up to speed. Let's remind ourselves where we ended last time. So we introduced the Laplace transform, and we showed, amongst various other properties, that applying the Laplace transform to an initial value problem, such as this one right here, turns the initial value problem into a inverse Laplace problem. So solving initial value problems turns into find me the function y whose Laplace transform is this right here, 9 over s squared times s plus 3 plus 1 over s plus 3. So instead of find me the function y, whose derivative plus 3 times itself is equal to 9 times t, where at 0 it's equal to 1, it's instead find the function that Laplaces to this. So that's the power of the Laplace transform in terms of differential equations, right? We saw that taking the Laplace transform of a derivative will undo the derivative. And we verified that all of our usual functions Laplace very nicely. We noted that there are some functions that cannot be Laplace, such as e to the t squared, which is a very unfortunate function, to say the least. But so our usual... The usual suspects can be Laplaced. And so now we're going to go in reverse. So sort of the same way in calculus where we learned derivatives and then we learned to go in reverse with antiderivatives leading into integrals, we're now going to go, alright, well, instead of given a function, find me the Laplace transform, now we're going to talk about given a function, what Laplaces to this. Okay. So a function f of t is the inverse Laplace transform of f of s if the Laplace of f of t coincides with f of s, capital F in that case, right? And again, like I said, def by parentheses. It only gets worse. But anyway, so if the Laplace of f of t is equal to f of s, then we will write that f of t is the inverse Laplace, so Laplace inverse of f, capital F, equals lowercase f. Okay. Now, because we've painstakingly verified a wide variety of properties of the Laplace transform, we now have a wide variety of properties of the inverse Laplace transform. So at the bottom here, we see the inverse Laplace is linear, and the inverse Laplace of certain terms gives us our usual functions, right? We know the Laplace transform of t to the n is n factorial s to the n plus 1, so the inverse Laplace of n factorial of s to the n plus 1 is t to the n. Right. So on and so forth with e to the at, sines and cosines. Okay, now let's compute a couple so we get a flavor for how they're going to work before we go off the rails, because as you're going to see, inverse Laplace can get it's going to get spicy. But before we get there, let's do a couple to get a feel for primarily to get a feel for the sort of constant trickery that is needed for these. So, for example, if you want the inverse Laplace 1 over 4s plus 1, right, that doesn't immediately look like any of our usual transforms until you remember the linearity, and then you go, well, I know what 1 over s minus a is going to do, so let me make it look like that by factoring out that 4. Okay, and then now 1 over s minus a, inverse Laplace is the e to the at. In this case, the minus a is a minus negative 1/4, so there we go. Okay. Alright, and similarly here, if I have 5 over s squared plus 49, now that almost looks like sine, right? Sine's inverse, so the Laplace transform of sine of kt is k squared over k over s squared plus k squared. So for sine of 7t here, right, because we see 49, we recognize that as 7 squared. That 5, pull it out, who cares, it's not useful. Now here, I need a 7 up in top, So the dirtiest math trick in the book, we multiply by 1, and we're clever about how we pick 1. Okay, so we can then factor out this 5/7, and then we get, hey, Laplace transform of 7t is this, so the inverse Laplace of 7 over s squared plus 7 squared, sine of 7t. Okay, so that gives us a little bit of a flavor of how inverse Laplaces are going to work, especially with the constants, because pretty much every problem you're going to run into with inverse Laplace, you're going to have to do something with the constants, so this is just, let's get used to this. But let's go back to our initial value problem. We converted it into this, find the function whose Laplace transform is that. So in other words, we know the inverse Laplace transform, just like the Laplace transform, is linear, so it breaks up like this. So now I need to compute two separate inverse Laplaces and add them together. Well, one of them is for free. One of them is like, there's no work to be done. E to the negative 3t. Yeah, that's, you can just read that off. There's nothing crazy we need to do there. Now, the other term, though, alright, now this one, this inverse Laplace, right, at first glance, it doesn't seem like this is going to be anything reasonable, right? It doesn't look like anything that we've seen. So what are we going to do? Well, if I look at it for a moment, and I think about it, and I let my mind float back to my glory days of Calc 2, where I, too, did very terrible as well. I'm not going to tell you what grade I got, but let's say it involves the letter D. Which isn't too bad. One of my very good friends is a professor at Carnegie Mellon, and he failed Calc 2 3 times, so you're going to make it, don't worry. Anyway, so yeah, you let your mind flip back to Calc 2, and then you remember something about things that look like this. And you're like, oh yeah. Oh yeah. Partial fractions. Yeah. Fine. Let's do it. So, alright. Now, it's worth noting that I'm not going to bury you with the partial fractions. They are, unfortunately, a part of inverse Laplacing, but we're not going to go nuts. We are going to see some interesting ones, to say the least, ones that you didn't see in Calc 2. So it'll be a little bit interesting, but we're not going to go too crazy. But anyway, so the bottom, there are two terms, the s squared and the s plus 3. S squared, that is a irreducible that's been squared in the bottom, right? S cannot be factored any further, so we need to include the two terms, a over s plus b over s squared. S plus 3 is just s plus 3, so it's there. Alright, cross multiply. And now at this point, there are two methods to solve for a, b, and c. The method that I am partial to is multiplying everything out and then matching the coefficients, right? On the right-hand side, we have a polynomial in S, so the coefficients all have to line up. Not too bad. The other technique that you can use is plugging in values for S to eliminate terms to solve for A, B, and C. But, technically, you really shouldn't be doing that because the values you'd want to plug in, of course, are s equals 0 to knock out I just noticed that. To knock out that, you'd plug in s equals 0, which is precisely one of the values you can't plug in. So it works, it's fine, but it's I don't know. I've factored out matched coefficients. It always takes less work to do this, in my mind. Plugging in numbers and trying to solve it, it's so much easier to do this, right? Because I can read off three things to you, and then from there, it's not too hard to solve for A, B, and C. Alright, so now that we got A, B, and C, we've done the partial fractions. The inverse Laplace goes very smoothly. Goes really well, right? There's not much that I gotta do here. So it splits up like this, right? We solve for the coefficients A, B, and C. And hey, inverse Laplace is linear, so you could pull out any constants and break it down to whatever terms you want. Inverse Laplace of 1 over s is 1, inverse Laplace of 1 over s squared is t, and that's it. So I've got the solution using Laplace transforms, right? We converted this initial value problem into an inverse Laplace problem. Find me the function whose Laplace transform is 9 over s squared times s plus 3 plus 1 over s plus 3. Now we then applied the inverse Laplace transform, did some partial fractions, did the work, clean it up here, and that's it. There we go. Right, and you can verify that this is the solution. So, for example, if you were to attack this with our usual method of finding the integrating factor and going for all the work, you will arrive at this answer. So, there we go. So not only is Laplace transforms going to help us solve some challenging differential equations, especially when the right-hand side is something like a step function that we had seen earlier, it's also robust enough to solve other initial value problems that we've already seen and could handle. So not only is it going to extend our knowledge, it also will cover everything we've already learned. So it's a very robust technique, which is a good thing. Right. So although you may feel that solving this with our old method was a little faster, maybe. Maybe. Possibly. Anyway. So let's talk. Let's talk a little bit here. Now, the one that we just saw wasn't too bad, but there are going to be some inverse Laplaces that are difficult. And difficult in the sense of, let's see. So, for example, here's one for you. Okay. So that first term is easier to see than the other one. So the first one, right, when you first look at it, you might go, oh, great, what is that? Well, you need to recognize sort of two things going on here. The first thing is, if I didn't have that s plus 1, if I just had 1 over s cubed, well, all right, I know the Laplace transform of t squared is 2 over s cubed, so we have that. And then you hopefully remember, that seeing a translation in the s-axis means that I multiplied by e to a appropriate power of t, in this case, multiplied by e to the negative t. All right. So the first one is a little easier to digest, right? So whenever you see like an s minus a quantity to a power, right? Okay, that's going to be a Laplace transform of a t, power of t, but multiplied by an appropriate e to the at. All right, so that one isn't too bad, right? It's still a little tricky, right? And it's one of those that, like, you get an eye for these after you kind of do a few of them. You can kind of start like seeing like I need this to match that, and so it's going to be very much like how when you were first going through integration, you were first learning antiderivatives, where you gotta like pick up an eye for it, and it's right. It's not as turn the crank as you want. It's a little more finicky. It requires a little finesse, a little massaging. It's not impossible, but it is, it's a process. You're not just going to immediately be like, boom, 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 I got these. And if you do, great for you. All right. But, okay, so that first term, not too hard. All right, well, how do we even go about that second one, right? The first one I was able to kind of get around pretty easily. I saw an s minus a to a power, and, I kind of combined the couple of things that I have in my head about Laplace transforms, but this doesn't look like anything. This doesn't look like anything that we've seen. Oh, except that it does. Except that it is. And now we're going to do the thing that everybody loves. You know what I'm going to do. You know what I'm about to say. You know what's coming. And you just need to accept it. That this is part of your life. And that is completing the square. So many people hate completing the square, and I still, to this day, I remember, when I first had to, do it, and, honestly, I maybe I learned it in high school, I really don't know, and in reality, I didn't, use it until, well into college, I don't even remember, I even think, going through Calc 2 and going through differential equations, I think whenever it came up, I just, didn't even do that problem, I don't even know how to do this. It wasn't until my mathematical modeling class where we had to deal with a lot of quadratics in the denominator and doing some stuff there where I was like, oh, wait, this is really neat, Right, completing the square is a really powerful technique where you could take your quadratic here, and then now I have everything I need to know about the quadratic, right? Specifically, if I want to graph what this looks like, right? You start with s squared, and then you shift it horizontally, and then you shift it vertically. Completing the square is a really powerful move, and it's not that hard of a technique because you look at the coefficient on s, divide it by 2, so that's what we're going to get here when we square it. Now, what do we need then? Well, what we need is to, after we take this divided by 2, plus and minus the square of that in there. Alright, in this case that would be a plus and a minus 1, and there we go. Alright, so square this out and you can see it working. Completing the square, if you're really trying to learn how it works, start with s minus a quantity squared plus b, square it out, and then match up terms, and then I think you can really see how it's supposed to work. But anyway, so after we complete the square, now we see something that's getting a little closer to something we can handle, specifically, right, very similar to this where we see a thing cubed, and we want to inverse Laplace it. Here we see a thing squared, plus a square, by the way, that's 2 squared, with s and a constant on the top. So this is probably going to break up into a sine plus a cosine. Yeah, right, remember s over s squared plus a squared, and a over s squared plus a squared? Yeah, alright, so actually, even though at first glance this looked like a complete utter nightmare, it's not too bad after we've completed the square. Alright, so, like I said, do a little reviewing of completing the square. You are going to have to do it, so if you're not comfortable with the technique, look into it. And like I just said, actually multiply this out and see how it matches this. And I think it, like, once you do that enough times, like, I think you see, like, exactly how it's supposed to line up. But anyway, so now that we've done that, it can be solved pretty easily. Now, look at how I broke it up. Okay, so I completed the square to get this, and then now I split it like this, right? And I split it like that because the thing that's being multiplied by a, this will inverse Laplace to cosine of 2t times e to the t, right? Because of the shift here, the minus 1. And here, right, this will inverse Laplace to sine of 2t multiplied by e to the t for the compensating for the shift in the s-axis. So when I cross multiply it, then it breaks into this. A is 1, and b has to be 1 as well. And boom, there we go. That's it. Okay. So yeah, so take a minute, take a breath, make a plan, and do your best. All right. So. You're right. So look at how I did it. So it's worth noting that the way I broke it up here, you don't have to do it like how I did it, but right, I like doing it this way because this thing I know will inverse Laplace to e to the t cosine 2t, because it looks like cosine 2t, but the s axis has been translated, right? There's been this translation in the s variable. Same thing over here. Okay. Alright, yep, and it breaks up nicely and inverse Laplaces beautifully, and that's the story. Okay, so there's a couple of examples of some particularly sticky inverse Laplaces that I don't want to say will frequently appear, but as we've already seen, we've seen e to the t cosine 2t as a solution to a differential equation, so these can potentially show up, so we do want to be able to handle them. Okay. Alright. Now, speaking of things multiplying cosine and things multiplying by sine, let's take a moment to talk about some, not really frequently occurring, but some occurring enough inverse Laplaces that you may run afoul of. We've also seen t times cosine and t times sine as solutions. So let's look at their Laplace transforms. So here I work out the details. Remember, Laplace transform of t times something is negative the derivative, the Laplace transform. And this cleans up kind of nicely. Get this s squared minus k squared. And now here's the real power. If you ever see like an s squared plus 1 quantity squared, you're going to be dealing with a t times cosine term. And thus from here we can see the inverse Laplace of there giving me the t times cosine. Similarly for sine, if you see like an s squared plus 1 quantity squared with an s in the top, here's how you would handle that. There you go. Right. So these are slick. Like I said, these are real. These are real smooth moves. This is when you want to impress people. You show off this inverse Laplace, and they're taken aback. Like, oof, this person knows what he's talking about. All right, but so these are good. Just put these these are tools in your tool belt. You know, you may not use them all the time. You know, it's like that freaking like T30 bit or something. You know, you got it. You know, whenever you need that. You know, or like you have those like screws that are like the square heads, you have the square bits, and you gotta like use your square bit. Like, oh yeah, you got one of those kits that had like square bits. You're like, when the hell am I ever using these? My father-in-law is a carpenter, and I talked to him about this that sort of construction stuff all the time, and he went off on like a rant about how everything other than square bit heads for screws are worthless, and like he just went off about how flatheads are totally dumb, and Phillips is dumb, and it's like everything should be square bits because of he just rattled off a bunch of reasons about why square bits are the best. Oh man, yes. I just let him go once he started going. I'm like, he's got some opinions. Let him finish. Anyway, he kept saying they had really good bite. That was the one thing he went back to. It's like, oh, they bite better than anything. You get this bite. He kept saying bite. He's like 70. Anyway, all right. Well, so we just saw a translation in the s-axis, but as we've discussed with the Laplace transform, you take t variables and you convert them into a function with s variables. And so we've talked about translating in the s-axis. Naturally, translation in the t-axis is probably a thing. So recall this function to kind of kick this off here with the Laplace stuff, or this piecewise function. It's actually a translation of something that's called the unit step function, or it's also called the Heaviside function. So the function that is 0 up until 0, and then 1 from 0 and beyond. Heaviside is actually somebody's name. It's not like the function has a heavy side. It's like, no, it was like actually his name, Oliver Heaviside, if I remember right. Anyway. So the function that we start with here is a translation of the unit step function. Specifically, it's right, you shifted it so that the step, the activation point, happens at 1, right? And in general, if you wanted to activate for any a, this is what you would do. So where e to the at translated the s-axis, we're going to see that this function translates the t-axis. So let's see that in action. So specifically, if we were to look at f of t minus a times the unit step function, t minus a, if we were to plug that into our Laplace transform, we'd get this. Note, this function does not activate until a and beyond, and when it does, it's just 1, so it kills off all of the integral up until a, and so we get this. And then now, doing a quick little change of variables, right, think about this, when we start at a, t starts at 0, right, start at a, so plug in 0, t starting at a, so that lines up. Quick little change. Then we see that I have an extra e to the negative sa term that I could factor out, right? The integral only cares about t, so e to the as can get removed, and ba-boom, there we go. So now we see that whenever a Laplace transform of f times e to the negative as shows up, we know what function got us there. That's pretty useful. So in particular, there's two things to get out of this. So something we'd actually already seen, which was the Laplace transform of that function at 0 up until 1, and then after 1 it turns on, is e to the negative s over a. Of course, that was a special case of something. Right? That's like something also in math. It's like anytime you figure out in a formula for something, it's like this is a special case of something. This is always a special case of some broader theorem. A very famous problem in mathematics was this thing called Fermat's last theorem, and basically it was asking x to the n plus y to the n equals z to the n. When is that thing going to have integer solutions, right? So x squared plus y squared equals z squared obviously has answers, Pythagorean triples, right? 3, 4, 5 for a quick example. And it turns out, though, that if you change the power from squaring to cubing, there are no more non-trivial integer solutions, right? You can plug in zeros and ones, but other than that, there's no way to make it work. And in fact, for fourth powers, there's no way, and for fifth and for sixth and for seventh, so on and so forth, there are no non-trivial solutions. And, right, you could just state that, and it's like, oh, yeah, well, there you go. But it turns out the way to solve it is using modular forms and elliptic curves, and it turns out just to be like a special case of like some other more convoluted stuff. So you know, you might stumble upon something and go like, what is this? And it turns out it's a special case of some, you know, massively complicated thing. But anyway. Right, so from this formula we get this nice Laplace transform of the translated step functions. But like I said, the main power is going to be this part right here. This now lets us identify some pretty easy inverse Laplaces. So with that being said, let's give it a go. Suppose, like I proposed way back when in the first video, that you've got a mass spring system sitting at its equilibrium. Right, here you go. Mass spring, just chilling, doing its own thing, not moving, sitting at equilibrium. This, as we noted, introduces an external driving force, but not until t hits 1. So let's take the Laplace transform. So on the left-hand side, it will go very nicely. Right, remember the Laplace transform of the second derivative will be s squared times the Laplace transform minus s times the derivative evaluated at 0 minus the function evaluated at 0. But those are both 0, so they're gone. So just, you know, cleans up real nicely. And hey, just send the s squared plus 1 over, and now we've got find me the function whose Laplace transform is e to the negative s times 1 over s times s plus s squared plus 1, s times quantity s squared plus 1. Okay. So note how I split it. I pulled over this e to the negative s term. This immediately tells me that when I inverse Laplace, I'm going to have a shift in the t-axis, and I'm going to be multiplying by the unit step function here. Okay, so the first thing we need to do is take care of the partial fractions. I'm not going to bore you with the details. This is one that, these are like my favorite. These like clean up super nicely. So this one here, you can verify what, that this works by actually like combining the fractions, right? Multiply, right, s squared plus 1 on the top here, multiplied by s here. The s squareds knock out, you just get 1. Boom. Comes out pretty nicely. Alright, so you can work with the details on that. So now for the inverse Laplace of this, we have e to the negative s 1 over s, e to the negative s s over s squared plus 1. The Laplace transform of the constant function 1 gives me 1 over s, so e to the negative s times it gives me the step function triggering at t equals 1. Here I've got the Laplace transform of cosine, but it's being multiplied by e to the negative s, so it then is going to give me this term here. So the Laplace transform, so cosine, but now with this translation in the t-axis. Alright, so there we go. Now we see it, and it's a good time. Okay. Beautiful, beautiful, beautiful. Alright, so now we've seen a couple more inverse Laplace properties. And let's wrap things up today with a real, this is a true question. The Laplace transform of 1 gives me 1 over s. What's the inverse Laplace of 1? So in other words, I want a function so that its Laplace transform gives me 1. So in other words, I'm looking for a function so that when I look at the integral from 0 to infinity, e to the negative st times this mystery function, which we're going to call delta t, that equals 1. Okay. So like I just pointed out, this mystery function is called the Dirac Delta, named after a mathematician, physicist. And as we're going to see, it's going to take a little bit of work to create this thing. And it's going to be a little startling when we make it, and we're going to have to talk about it. But before we get into that, I do want to point out, before we get going, the Dirac Delta here is a great example of something that's hard for mathematicians, I think, to recognize, which is that sometimes physicists come up with good ideas. Sometimes physicists, they actually know what they're talking about. And specifically, the Dirac Delta was a great case of them cooking this thing up and solving problems with it. And mathematicians going, "What are these idiots doing? This thing is garbage." But they're getting right answers. So what are they actually doing? And then we'll get into it in a little bit. The Dirac Delta is really fun. But anyway, so I'm going to show you how to create this mystery function right here. So the first thing we're going to do is, for each positive integer, define the function delta sub n to be the following. So it's n times the unit step function minus unit step function shifted by 1 over n. And the right way to think of this is that it's basically just a rectangle. It's a rectangle with width 1 over n and height n, so it's got overall area 1. So specifically, when I slap it into the usual Laplace transform, right, what happens? Well, right, the only time it's not equal to 0 is from 0 to 1 over n, so it gives me this, that we know how to integrate and plug in some stuff and, do a little magic here, do a little moving things around, doing some math clairvoyance, because I know where we're going with this already, so I've already cleaned it up to make it go nicely. So what we're going to do is, instead of creating the Dirac Delta outright, we're going to create things that approximate the Dirac Delta and then take the limit. So these delta sub n's we've created, we've now set up this integral. Naturally, we're going to take the limit as n goes to infinity, and obviously what is the hope here? The hope here is that this limit goes to 1, so let's actually verify that that happens. Oh, it does. Okay, good. We can walk away now. Let's walk through why it does. Right, so the first thing to note is, if you do try taking the limit as n goes to infinity, what do you get? Infinity here, up here, we will get 1 minus 1, so we have 0. Infinity times 0 is a indeterminate form, right? Remember, infinity, you can't enforce algebraic rules of infinity because there's no consistency there. So, right, as we're about to see, infinity times 0 is equal to 1. Sometimes it's actually equal to 0. Other times it's equal to infinity. Other times it's 5. There's no hope with that. So, we're going to go to the hospital. We put the 1 over n down here, so that now when I do take the limit, I get a 0 over 0. So I can L'Hopital it, and then conveniently, the s terms knock out, the n squared terms knock out, the minus sign knocks out, and the limit just goes to 0. Boom, done. This is such these are this is one of those where like once you like do it and then you see like everything just cancels and then it's equal to 1. That's when you realize the math gods are just cruel. They put math here for us, just for us to suffer. Anyway, so as promised, the limit indeed is equal to 1, so we'll then define the Dirac Delta to be the limit of these delta sub n's. So it's a lot, like I said, it's a lot easier to approximate what the Dirac Delta is and then take the limit, because now when we take the limit, right, the delta t, the Dirac Delta, well, those are the limit of these delta sub n's. Pull the limit out, then we have the limit of this thing. Well, we know the limit of that is equal to 1. We just proved that. So there we go. Our mystery function, whose Laplace transform is equal to 1, is the Dirac Delta right here. Excellent. Okay. Now, like I said, there's something we got to talk about here. This is not a typical function. Right, so note the way we created it. We created it by taking a limit of other functions. So you took a sequence of functions, right? So instead of a sequence of numbers, a sequence of functions, and then we took the limit of those things. But if we look at the inputs, what happens when you take the limit here? Well, n goes to 0. So this here is this rectangle, right? Really skinny rectangle, 1 over n. Really skinny, really tall. And as n goes to infinity, that rectangle gets stupidly small, right? It gets so thin, it disappears. But at 0, it won't. At 0, it gets infinitely large. So if we were to think about it as a normal function, it's 0 everywhere, except at 0 when it's infinity. So it's not a function in the usual sense. Instead, it's what's usually referred to as a generalized function. The fancier name for it is a distribution, where basically it's not a function per se, but it's something that can be reasonably approximated by functions that are nice enough so that when I take limits, things do what they're supposed to. So physicists were just doing this, specifically Dirac, and mathematicians were laughing at them, going, "Look at these idiots, just taking limits like that works." And then mathematicians had to, stop and go, "Oh wait, it does work. Wait, what are they doing? Wait, what? Why does it work?" Which, yeah. There was this break that definitely happened in the 1800s. In the 1700s, mathematicians and physicists, they were like one and the same. They were like just taking limits, divided by 0, just who cares, just do whatever you want. But in the 1800s, mathematicians really started moving away from, you really got to rigorously justify things before you just do stuff. The Hawkman himself, Stephen Hawking, very famously said, "I'd rather be right than rigorous." That's his opinion of mathematics. Well. Oh well. All right. So it is worth noting that the theory of distributions are really neat. I did a graduate class on distribution theory, and it is some cool stuff. It's really neat, but it requires some high-powered mathematics. You have to. So it's part of a branch math called functional analysis, which is my jam. That's my stuff. That's where you combine calculus and linear algebra together. And part of that is this theory of distributions, which gives you these really powerful tools to solve differential equations. So we're kind of getting a little taste here. The Dirac Delta is the classic example. There are some other examples of distributions, but the Dirac Delta, that's the main one. Beautiful. So I'm going to give you a parting shot for today. So the Laplace transform of the Dirac delta is equal to 1. It's going to also be useful to know the Laplace transform of the Dirac delta, where I think I've said the Dracula delta. just start calling it the Dracula delta. I should do that. I'm at a conference and I'm just like, the Dracula delta. See if anybody notices, raises their hand like, "Wait, excuse me, what are you talking about?" Well, my name's Christopher Lee. I'm allowed to talk about Dracula whenever I want. And that reference, I think, is getting a little too old, just like me. I had a professor on the older side. When the first time I went to his office, he asked what my name was, and he was like, "My name's Chris Lee." And then he went like, "Oh, okay, that's an easy name to remember. I'll just remember that you're Dracula." Yeah. So for the for you Zoomers, I guess the closest thing would be Count Dooku. So anyway, all right. So recall this Laplace transform formula right there. Now the Dirac delta is 0 everywhere except that 0 where it's infinity. So if I were to shift it, well, then that means the infinity point is happening at A. And so if we're going to multiply that by the Heaviside function, it's still going to be the Dirac delta as normal. So by a quick application of this formula, since the Laplace transform of the Dirac delta is 1, we see that the translated Dirac delta, its Laplace transform is e to the negative as. Nice. Okay. All right, and with that, closing in here, perfect 40 minutes. Excellent. So with that, we've covered all the ins and outs of inverse Laplaces. So next time, we're just going to do a couple of examples, and then we'll call it a chapter. All right, sounds good.